Antique pewter is a mixture of 85% tin and 85% tin and 15% lead. Antique pewter, this particular kind of pewter, will get dull with time because just sitting in the atmosphere, there's enough lead in it, only 15%, but enough lead in it so that you make a lead sulfide, and the lead sulfide is a dark color, and so it will discolor with time. But it's easy to cast. It's almost a eutectic composition. It's easy to handle and make all sorts of floral castings and beautiful combs and mirror backs and all sorts of things like this. Mugs, beer mugs and plates and whatnot. And the people of yore used an awful lot of pewter. And so people collect pewter as an antique. It's very difficult to find a piece of this antique pewter, and there's a reason for it. You see, let's take this country. Back in the olden days, if you lived in the frontier and you were, say, had a pewter plate, a family had pewterware, they ate out of it. It's a relatively soft material. If you go slicing into the plate with a knife, you could cut it up and scar it up. It was soft. You get it bent up and you're washing it or banging it over each other's head or whatever you do, and it got beat up. And so you'd like a new plate. Well, along would come a guy that would be called a tinker who repaired things, and he would carry with him a set of molds, like plaster Paris molds, in the shape of a plate. And you'd get your pewterware, melt it down, cast it into this mold, separate the mold, take out a brand new plate. So the old beat-up plate, the piece of antique, always got replaced by recasting and recasting. This same tinker, by the way, did an interesting little thing I like to tell you about, because he repaired kitchenware, all sorts of metals. Because this material, pewter, is a solder, and it's easy to use, and so he frequently repaired holes in pans with it. When he did that, he'd take the hole in the pan, he'd take a little bit of clay, and he'd build a dam around the hole. And then he'd put a piece of clay on the bottom so that the molten metal wouldn't run through the hole, and he would cast the metal in the top. It would make a little plug in it with a swollen end on the bottom side and the top. And when it was all through, he took the little dam off and he threw it away. So the expression, not worth a tinker's dam, the dam isn't spelled D-A-M-N, it's spelled D-A-M. It's that little piece of clay that's no good for anything. So you see out of this field of metallurgy come all sorts of exciting words that we use every day, and we don't know where they come from. It's just exciting to know. At least I think it's exciting to know. But how about the pewterware? Have you got a piece of pewterware? If you have, are you sure it's pewter? Because if it is, it should be 85% or greater tin in it. And if you bite it, it'll make a noise. And so in the little community I live in, I'm known as a pewter biter, because I go visit people and they say, oh, I bought a new piece of pewter, antique pewter today, would you like to see it? And they give it to me, and the first thing I do is stick it in my mouth and bite it. And it makes a noise that goes through the bones of my head. I hear it, and I said, well, yeah, that's antique pewter. But most of the time these days, it's not that material, and it doesn't make a noise. So if it didn't make a noise, you see, the old bartender says, hey, that's a good piece of coinage, and if it did make a noise, no good. It's got to be counterfeit.
Mechanical properties of non-ferrous metals vary across an equilibrium diagram. In a solid solution diagram of copper and nickel, for example, ultimate tensile strength reaches a maximum at the midpoint of the diagram. A eutectic diagram, however, shows ultimate tensile strength varying in a simple linear relationship. When tin is elastically deformed, crystals are pushed out of equilibrium, flipping over to relieve strain. This is called twinning and accounts for the cracking noises made when tin is bent. Tin and lead compounds have many uses, among them soldering materials and pewter.
Well, I know that's a long way to tell you a story about tin, but the non-ferrous materials sit out there, very serviceable to us in many, many ways, and we utilize them in a lot of different ways. And your text is going to discuss primarily the engineering applications of these materials. And it's so simple to read and so easy to read, I'm not going to discourse too much on what the book has to say. I don't think it really needs any explanation. I would like to, however, tell you about a little bit more about some of the materials that are not really pursued at length. So I'd like to take you gold mining, if you would listen to me, because it tells us something about what went on in this country, what goes on in the world, a simplicity of things that happen, and enable us to see in what we're going to talk about in this and the next lesson, of how we extract the material from the ores. Well, let's suppose for a moment that you were a prospector and you wanted to go find a metal. As we said in the first lecture, one of the easiest things to find would be a metal that's a native metal, that's going to exist just like it comes, like copper or gold or silver, or maybe even mercury. But most of the time you're not going to find it in that particular form. You're going to find it in a dirt or ore that looks like it's contaminated. It's not a native material, it's a native metal. So if we were looking for gold, we would go find, let's say, a gold-bearing sand. And we may suspect that it has gold in it, but it may be tiny little pieces of gold, and we'd have a hard time ever finding out how much the whole mess was worth. And so what we want to do is to learn how to take it out of that conglomeration and reduce it to a piece that we could put our fingers on and say, see my hunk of gold. Well, how do we do this? Well, the processes that we use are so similar across the board for almost everything that we have. I'd like to sort of in detail now tell you what you would do as a prospector if you went out and, say, found gold sands or a sand or material, an ore that you say suspect is going to be high in gold. And I'm going to do this by explaining two things to you. Number one, how you beneficiate the ore. Remember earlier we talked about beneficiating the iron ore, right? Well, we're going to get this ore, and what we want to do is to get it into a condition that we can easily extract this material, this non-ferrous material. It's called gold. So it's going to have a lot of sand with it, but the gold is going to be in little teeny particles now everywhere in it. So what would you do to separate it? Well, one of the heaviest elements that we have in the periodic table, not the heaviest, but one of the heaviest, is gold. And so if there's anything lighter than that, we ought to be able to float it off. Most minerals, most metallic minerals, and most of the minerals we have are metallic minerals, are heavier than water, and they don't float. So what we have to do is to give them a little boost, give them a push, and so we cause a convection current in the water. When the prospector pans the gold, and he swirls it around in the pan, the gold, the sand, the water, what he's really doing is putting a force field on it that will sweep out the lighter particles first and leave the more dense particle. It's gold. Well, you could build an apparatus now so you percolate water through the ore. But I want to separate this tiny little piece of ore, piece of gold, from the rest of the ore. So what is the first thing you'd expect that you'd have to do? Chew it. Masticate it. Crush it up. You dig out a great big hunk of rock, you think it's got a lot of gold in it, you want to mechanically separate the parts. You do exactly what you do when you want to get the food value out of your food. You just chew it up. You break it up into tiny little pieces so you can now operate on it. When you do that, you'll find that some of the little pieces are going to be pure gold, and some of the little pieces are going to be not pure gold, but let's say the gangue material, G-A-N-G-U-E. That means the debris, the stuff that is not the ore you want. So this gangue material, which will not have any gold in it, will be floated off. And then there's a group of little particles that will have a piece of gold in it and a piece of gangue material, and you want it to settle on the bottom. You don't want to throw any of the gold away. But now what we have done is concentrated the ore. This is ore beneficiation. We have tailings, or a pile of material over there that we washed out in this hydraulic jig. And when we did that, we say, oh, my gracious, now I can take the material that's left and I'll find out how much gold I've got. So we can go through the process now that the man who would be called the assayer would go through if you lived in the 19th century and not the 20th century. And he did something called fire assay. Well, he may not have gotten that piece of gold because the miner has another little trick he could do, and he could do something that's called amalgamation, process of refining the gold. And he'd take a copper sheet, another non-ferrous material, and he would amalgamate the surface. That means he makes a pad of mercury on the surface that'll stick to it. If you turn the sheet upside down, the mercury would just hang on by its own surface tension. So we have this sheet that's covered with a liquid metal, and he would cause the little particles of gangue material and gold that's mixed to tumble down this washboard, if you please. And every time the gold rolled around and touched the mercury has an infinite solubility for gold. You know, you put mercury on your ring, it turns it nice and silver. Well, if you do that every morning, your ring will eventually splash. You know, it'll just turn, you'll have gold dissolved in the mercury. And so the mercury will just wet the gold and then dissolve the gold. It'll hang on to that little particle until it dissolves all the gold out, and then the water will wash the gangue material on by. So you could collect it as a mercury gold amalgam. As soon as this pad of mercury got pregnant with gold, you'd scrape it off with a hoe, with a squeegee, and put a new amalgam on it, continue the process. But how do you get the gold separated from this mercury? Well, that's pretty easy, because all we got to do is to heat it up. The vapor pressure of mercury is very high, and the mercury will boil off. And when it boils off, all you have to do is to cool it, and it'll turn back to liquid mercury. Just put it through a little still. That's all you have to have, and you can convert it back. So this is called the amalgamation process of refining. And it's used, by the way, on a large scale. Still in Alaska today, I understand, they do a lot of amalgamation refining. Well, let's suppose we turn back to the fire assayer now, and you've taken him in this sample of your ore that's concentrate, and he wants to find out how much gold is in it, or how much noble metal is in it. Gold, platinum, palladium, iridium, rhodium, all of those things, which are noble metals. A little trick that he would do is, he would first of all say, there may be some metals in there which are not noble, but are in an alloy with the gold. And so what he will try to do is oxidize it out, because you see you can't oxidize the gold. It's a noble metal. So he puts all of this in a little crucible, and he puts it in a furnace and brings it up to a very high temperature and oxidizes it, scorifies it, or turns everything that's metallic to a metallic oxide. If you happen to have some sulfides in this process, they're going to go off as sulfur dioxide into the atmosphere. But when he's finished, he's sure of one thing, that is, everything that'll oxidize is oxidized. Strangely enough, we normally think of acids and bases as some liquid that you pour out of a jug. I guess that's because of the way we're educated. You know, if I want an acid, I'm sure it's going to be in a bottle, right? Or in a liquid form. And if I want a base, I'm sure that's going to be in a bottle. But the fact of the matter is, we know, if you just stop, if you don't play Amos, just stop and think about it, you know that that's not so. Because every morning you eat a little acid, maybe, called ascorbic acid, right? Vitamin C. Or you see citric acid, which is a solid. Or if you've ever seen stearic acid, it's like a bar of soap, right? It's a solid material, stearic acid is. And so we have acids that are solids, and we have bases that are solids. Well, you know that if you've ever seen a can of lye, that's one of the best bases we have, sodium hydroxide, and it's a solid. Well, how about a material like silicon dioxide? Is that an acid or is that a base? That's an acid. That's right. Up at high temperature, that's an acid. And a base would be oxides of a lot of the metals, like iron oxide, calcium oxide. They're bases. So since I've converted everything that's in this scorified mass that I want to assay into an oxide, what I really want to do with it now is I want to put with it a material that will make a reaction with the oxide. That means I want to add a siliceous material, a silica-bearing material, because I'm sure I'm going to have these earth oxides. That means I'll put in something like sand and borax, and then I want to reduce the oxides if I can, and so I'll mix a little charcoal with it. And I want to make sure I can gather it all together, so I put some litharge with it, some lead oxide, because the charcoal will reduce the lead oxide and give me elemental lead. And gold will dissolve in the elemental lead, so will silver, platinum, palladium, iridium, and rhodium. And so I'm going to have a situation so I can put the charge in the furnace, heat it all up to high temperature, I'll get this reaction to occur, and when the reaction occurs between